Chalu? Okay. Yesterday, we described in detail an example of what is called the large N expansion. There was a set of scalar fields which has an index 1 to n, and this had an ON symmetry. And then what we did was introduced a singlet field which appears as a Lagrange multiplier. So we had an action I'm writing symbolically. And then we noted that I sort of massage it like this. N upon g square n, and this became n times something, some functional of sigma. It is important that n came out as an overall factor, and the reason why it eventually came out as an overall factor is because we wrote everything in terms of the combination g squared times n. So that allowed us to take a limit n tending to infinity, g tending to 0, g squared times n lambda is order 1. But since n was in front of this, we could use a saddle point approximation to evaluate this functional integral. A saddle point approximation is pretty much like a classical limit. When you do Feynman path integrals, where this is the trajectory of a particle which joins 2 points. This is the expression for the quantum mechanical in elementary quantum mechanics. There is an h bar which is stuck below here. This h bar is necessary to get the right answer. There was an h bar here as well. And we usually talk of the classical limit as a limit where h bar is small. But of course, h bar small doesn't make much of a sense. So typically in a given problem, we combine h bar with some other dimensional quantity which has units of action to make it into a dimensionless variable. The important point is this h bar came here in the denominator. So in a suitable sense, when h bar is small, this s is multiplied by a large number. Of course, there is an I sitting here, which is the difference between real time and Euclidean time, but that doesn't quite matter in the theory. So it looks like that this 1 upon h bar is on the same footing as capital N in this theory. So the first thing I'll do is to make this statement a little more precise, and we'll have an important lesson to learn from this statement. So let us take some general large N theory, and let's compute the generating functional for correlators of operators which are B of x. B of x is a singlet operator constructed out of phi. For example, I can take B of x to be, so phi I of x, phi I of x, because of the sum upon I, this is invariant under the ON symmetry transformations. Okay. I put a factor of n here, and I put a factor of n there. I put the factor of, no, I don't put a factor of n here, but no, that's okay. Let me put that way. So to keep track of factors of n, we already argued that this functional integral, if I write this as exponential of minus f, f is like the free energy of the theory, but it contains a j, f is order n. Okay. If j was 0, we provided an example of how it becomes that is f becomes of order n. That was the example which we did last time. But nothing in that argument changes if I add a term which is an n times an order 1 object. The division by n has made it into an order 1 object, and a term which looks like this, with some arbitrary g of x. So the same argument holds, and f is the order n. However, this object is the generating functional for correlators of this object B. In order to see that, if you compute, so correlators like B of x1, B of x2, pardon? Yeah, so the guide to that is to count how many terms are here. There are n terms, that's why I divided by n. If I mean, later on I'll discuss things with matrices where there are n square terms, then you have to divide by n square. So if I calculate this correlation function as an average in this functional integral, then by definition this is going to be singlet. Singlet means it is invariant under the symmetry group. The symmetry group was the group, orthogonal group ON. Okay, so this is like a square of a vector. The square of a vector doesn't change under rotation. Okay? Yeah. Del n log j. Yeah. So the idea behind this is that every time you take a derivative with respect to j, one factor of b comes in, but it comes in with a factor of n. And every time I keep doing it, I'll bring in down and down more factors of this. And at the end of the day, I have to divide by 1 upon z to actually get the average. If I am interested in the correlation functions of the theory which is just defined by S of phi, I'll evaluate this and put all the j is equal to 0. Oh, then you didn't, sorry, I should actually. just say. There is a notion of what is called a connected correlation function. And what it does, it takes, for example, the connected correlation function bx1, bx2 connected is the full correlation function. If I take b of x1, b of x2, b of x3, this is going to be b of x1, b of x2, this is connected. The regular one plus minus minus plus permutation. So basically the idea is you take the full answer and subtract from this anything which is a lower order correlation function multiplied by what is left. So that's the idea. I will not show this, but you can look any field theory book, and what you discover then is that the connected correlation function is simply given by just this object. It's actually quite easy to prove that this thing is true. So log of this generating functional is the generator of the connected correlation functions of the theory. This relationship tells you something extremely interesting. It's quite a trivial relationship. So what this tells you is that you already know that for a large n theory, log of z is of order n. This tells you the order of this thing is n raised to the power 1 minus small n. So let's try to examine what does this mean for a few correlation functions. So that therefore means that bx1, bx2 connected is this is definition. So this means, but however by this formula, if I use this formula for n equal to 1, that means b1 same as b2 is order 1. When I write b1 actually means I'll sometimes use the notation like this, b1 b2 connected is order 1 upon n, right. So this tells you that this is a property of generic large n theories. It has a name, it's called factorization. What does factorization mean? I will argue that factorization actually means that in terms of suitable variables, there got to be a classical field theory which gives you the complete answer for the highly quantum field theory at large n. What is the situation when averages factorize? square by 2m plus v of x. And if I calculate, say, correlation function of some operator, or the average like this, for example, I calculate x of t1, x of t2, in something like that, then of course it is not correct that this is the same as the product of the averages. It's because there are fluctuations in the theory. However, if the theory was classical, in the classical limit, it got to be true that O1, O2 is equal to the product of O1 average times O2 average. That is the meaning of a classical limit. Okay? In fact, this is typically, the reason why this happens is because O1 and O2 are made out of operators P and X which do not commute. Their commutator is order h bar, and therefore when you commute that through, you are going to get some factors of h bar. And it's not very hard to see that this is this plus order h bar. So what this relationship suggests is that the n equal to infinity limit is some kind of classical limit. It is not the classical limit of the field theory we wrote down. We did a functional integral over phi. We actually did the whole functional integral non-perturbatively. We didn't write down classical equations of motion of phi and did something with it, right? But nevertheless, this seems to indicate that there got to be a formulation of the theory in which I can just do classical physics and get the full quantum answer for large N. This point clear? Yes. Minus x O1. Yeah. Okay, so let me give you, let's solve quantum mechanics 101 problem in a clever way. You all know how to solve this. Good point. You will be surprised how good this approximation is in certain cases. So let me tell you a little bit of history of this thing. This thing was, I think, first found in statistical mechanics as just a trick to approximate. If suppose you want to calculate something in the O3 theory, you cannot do it, so you do some approximation in ON. But then you can think of this as spins living in very high dimensions. If I have a vector which has n components, like the things I started out with, you can think of that vector as living in not in 3 dimensions but in n dimensions. It's solving an n dimensional problem. Okay, but this thing really actually came to almost like its zenith due to a beautiful work by Gerard 't Hooft in the 1970s, who asked the following question. 't Hooft was interested in the theory of strong interactions. The theory of strong interactions is a non-abelian gauge theory which has a symmetry group, which is like SUN. No, doesn't matter, SU3 doesn't matter what SU3 is. If you don't know it, don't know it. Who cares, right? And so for various reasons, now this is a very difficult theory to solve. I mean, nobody knows how to really solve it. People use all kinds of approximations to do this. However, there was a lot of experimental knowledge about strong interactions. There was a lot was known about how things like mesons and baryons, the strong interactions the basic elements of strong interactions are things which are called quarks and gluons. You know, quarks are fields which pretty much like what we wrote down here are fields which have an index I, that I runs from 1 to 3. That's why it's an SU, it's a complex, typically a fermion, that's why it's an SU3 gauge theory. And gluons are no matter what, forget about what gluons are. Okay. The point is that in nature, we don't see free quarks. I mean, you can't isolate a quark. You cannot take a quark out of a proton or a neutron, which is a bound state of 3 quarks. And then there are the things called mesons, which are bound states of quarks and antiquarks. And when people looked at the experimental results for scattering of things like mesons, they found it's a very good model to take a meson as a quark and an antiquark which is joined together by a little string. So this thing flops around, scatters with another thing, the string can join with each other, and that explains to a very good degree, at least to a certain degree in some cases, in fact, quantitative aspects of strong interactions. Okay. Except it was not very clear how to get this from this SU3 gauge theory. So the idea arose that what is really happening is that quarks have this new kind of charge which is called color. You know, just like if you have a charged object, a typical charged object, you draw pictures in textbook with fields of lines of force which look like this. One way of thinking about it is that the flux, the electric flux of which comes out of a charged object spreads out evenly, spherically. That gives rise to a potential which is 1 upon r and the force which is Coulomb's law. It has to be uniformly spread around in order to have a Coulomb law. Okay? If there were magnetic monopoles in nature, the same thing would happen to magnetic fields. I mean, magnetic fields would have just spread out, just like the analog of charge fields. Okay? Now, there are examples known where magnetic fields in nature do not spread out, but they are actually collimated in tubes. These things happen in superconductors. A superconductor is an object where there is Meissner effect. It does not allow magnetic field to go through. So if you try to force in a flux through that superconductor in things called type 2 superconductors, the flux, instead of spreading out, gets collimated into little things. These are called Abrikosov vortices. So the idea arose that it must be true that the QCD vacuum is such that it collimates this electric kind of fluxes. So it appeared as a thing like this. Okay? So that was the origin of string theory. I mean, this was the model. It's called the string model of hadrons, which was developed in the early 70s. Except the problem was that when we talk about any theory as a theory of particles or a theory of strings or a theory of membranes, we always have in the back of our mind a small number. And when that small number is really 0, the objects we are talking about are free objects. If the objects, if there is no limit, when these objects are really free, then it really doesn't make sense of talking about particles. For example, an electron, we think of it as a point particle, right? To a very good approximation is a point particle. But if you think about in a quantum theory what an electron is hardly a point particle. It's a pretty big blob, of not very big, but a small blob, which is caused because of vacuum polarization, pretty much like what happens in a dielectric. In the vacuum, that same thing happens. So it's a big fuzzy object. So why is it we can still think of electrons as point-like objects? The reason why we can think of electrons as a point-like object is because there is a small number in the theory of electromagnetism. That small number is called the fine structure constant. And this number is like 1 upon 137. If this number was big, there was no chance we could have approximated the electron by a point-like object. So the problem we took face was to try to understand that if this picture is working so well for quantum chromodynamics, which has an SU3 gauge symmetry, what is the small number? Where did the small number come from? And you look at the theory, there is no chance that there is any number, any dimensionless number in the theory. So 't Hooft, being a brilliant man, he invented a number. He said, let's replace these 3 colors by NC colors. And let's take the limit that NC goes to infinity. It's a mathematical limit which you think about. Okay? And then he showed that in this limit, that these objects, these mesons, or the equivalently the strings, are free in the limit when NC is very large. So it gave you a kind of a physical meaning of this limit. If you ask in that theory, what does this limit mean, NC going very large? This is the imaginary limit of your theory in which mesons and baryons are free. Okay? So there you go. I think it's a pretty physical answer to your question. Okay. So let's proceed with this. Wave function, the many body wave function, not necessarily. When written in terms of, I'll come to wave function and we'll see that it written in terms of appropriate variables it does. So let's solve a quantum mechanics problem. So the quantum mechanics problem we want to solve is an isotropic harmonic oscillator. So I'm solving a Schrodinger equation. In n dimensions. So you want to solve, I'll put h bar equal to 1 just to see what is happening, just to in fact emphasize acting on some wave function is E psi, and my problem is to solve for the various possible E's and the wave functions. The wave functions are a function of x1 to xn. Everybody knows how to solve this problem? Right? Everybody knows how to solve this problem because these are n decoupled harmonic oscillators. You solve them one by one, find the wave function, take a product of the wave functions, and you get the answer. Okay? But then you can be a little more little smarter about this and say that from that answer, so this is roughly the wave function is like psi 1 x1, psi 2 x2, and so on and so forth. Forget about these and so they clearly in this, I mean, each of them is some, what are they called, harmonic polynomials or whatever they are. The energies are sum of these harmonic oscillators. But one thing this way of writing doesn't do is to tell you what are the properties of the wave functions under the rotation group in n dimensions. You're sometimes interested in knowing that. That problem also you know how to solve. You go to polar coordinates. That means you go x1 to xn to r and then n minus 1 angles. See, normally we do 3 dimensions, so there are 2 angles. Now there are n minus 1 angles. Very good. You make that change of variables in this psi, you write down an equation, you realize that eventually it's the square of the angular momentum, which those eigenvalues, you do spherical harmonics in n minus 1 dimensions and you die. I mean, spherical harmonics in higher dimensions are not very easy. Okay? But let's ask that I want to look at S wave functions. These are wave functions just purely a function of r. They are not functions of theta 1 to theta n. See, normally when you do 3 dimensions, then this equation, so what you write is, in 3 dimensions, you write r theta phi as some and this UL satisfies an equation m is 1, this is called a centrifugal term, and it just comes from the angular momentum. L is the same L as in the spherical harmonics which are sitting here. Very good. So if I am looking for S wave functions in 3 dimensions, I put L equal to 0, and the thing becomes very simple. It just becomes this plus that, and you can just go ahead and solve the equations. If you try to do the same thing in n dimensions rather than 3 dimensions, and look again at the analog of L equal to 0, what do you get? And I'll just write down that equation is the following equation. So in n dimensions, you define a radial coordinate with a factor of 1 upon n. Remember that B we defined there was a 1 upon n? The same reason I put a 1 upon n in here. And you define a wave function which is r raised to the power n minus 1 by 2 times chi. This is the analog of putting this 1 upon r for 3 dimensions. Okay, if n equal to 3, then 3 minus 1 by 2 is just minus 1, so it's 1 upon r. And this factor is of course a Jacobian factor which gets absorbed when I make a change of coordinates from Cartesian coordinates to polar coordinates. So basically in 3 dimensions I have dx1, dx2, dx3, that is given by dr, r square, and d omega 2. So if I take the inner product of 2 wave functions, psi bar psi, psi star psi, right, this inner product becomes a standard inner product with a standard measure dr if I redefine if I define r times psi is equal to u. That is the reason why you divide by r. That is why the Schrodinger equation doesn't have any funny things here. It's just a standard d squared by dr squared. The analog of the same argument just tells you that this power, that it has to be n minus 1 by 2. Okay? And then it's a simple thing of, if these are only a function of r, that's what we are interested in. That's what I call the singlet sector of the theory. Then you get an equation, which I'll just write down. This is the analog of that equation. I put L equal to 0, everything is only a function of r. And the interesting thing to note here is that there is still a 1 upon r potential which comes out of the problem unless the dimensionality is 1 or the dimensionality is 3. So luckily, I mean, we usually do with dimensionality equal to 3. That's why in the S wave there is no centrifugal barrier. This barrier is still there for other arbitrary dimensions, and it's not caused by angular momentum. It's just caused by that change of variables. Okay? Now let's take the limit n going to infinity. So there are n minus 1 is the same as n minus 3 is the same of n, there is n square upstairs, n square downstairs, that cancels out. Okay? Now stare at this for a moment and compare it with the standard Schrodinger equation in your favorite book which has h bars in it. Okay? That Schrodinger equation is h bar square by 2m d square dx square plus v of x psi equal to E psi. Good? So it is clear that 1 upon n plays the role h bar. Okay? So just as when all other actions in the problem are small compared to h bar, I can solve the problem classically. That's the classical limit of the theory. So there, by being classical limit of the theory, if I, for example, if I was looking at the ground state, classically, I'll just minimize the potential. Let us look what the potential is and minimize it is. If it is a harmonic oscillator, it's at x equal to 0. So therefore, for this problem, I should do exactly the same thing in the n going to infinity limit. I should find that I get a very good answer if I just take this potential and just minimize it. And it's an easy calculation. I suggest that you do it. If you look at this potential looks like that. There is a minimum, and that in fact indeed is expectation values. And at that point, so there is, what I have therefore found is a classical theory which is completely equivalent to this quantum theory. That classical theory has a variable which is r. It's a singlet variable, doesn't carry any of these indices I, and it has an action which basically, if I try to write down what the action for this thing is, the action is going to be integral dt half r dot square into minus v of r, where v of r is given by so this is one way in which a large n limit is a classical limit. It's quite explicit in this problem. Okay? Yes. No. H bar has been set to 1. Right? The same reason why you retain h bar. What this means is that the momentum operator of this theory is given by minus I by n ddr. That's what the Schrodinger equation tells you. And the commutator of P and R and this momentum operator is 1 upon n, I upon n. No, because it's the same reason why when you do quantum mechanics, you just take the classical potential and stick it in the Schrodinger equation, right? If you were to, this is good enough for the, what I've done here is to just demonstrate that the large n limit is the classical limit. If you were interested in carrying out corrections to 1 upon n, this is of course not good enough. Then you have to take the 1 upon n corrections which come from the potential, and there are various points of 1 upon n corrections. And I'm not worrying about that at the moment. But there's a completely systematic way of doing this. Okay. Good. So let me give you a very simple application So what you have is the dynamical variables is a single matrix which is a function of time. So I and j runs from 1 to n. This is a Hermitian matrix. And as Shotto has been explaining how to deal with such matrices, if you ask what is the natural symmetry which works on these Hermitian matrices, it's a unitary group, UN group. And so since this is a thing like this, I can write down an action which is trace where V of m is like a polynomial, C1 times m square plus C2 times m fourth, you know, what have you. The trace makes this thing invariant as it should be. And you want to do exactly the same thing as I showed for the isotropic harmonic oscillator in n dimensions. What you want to do is to take the limit n going to infinity, and typically there is a coupling constant in the theory, and you want to take g square going to 0 with g square n held fixed. And then you got to figure out what are the invariants of this theory. So what are the analogues of that radial coordinate, right? When you had a vector, n component vector, it was quite obvious what is the radial coordinate. It's just one of them, right? It's the sum of the magnitude of the vector. The property of the radial coordinate was the radial coordinate was invariant under the symmetry group of the problem, which was On in that case. Here, so you got to ask, out of that matrix, what are the singlet objects which I can make? And then you immediately realize there are an infinite number of singlet objects, basically at large n. They are things like trace m square, trace m cube, you know, all the way you go up to trace m to the n minus 1, and the next one can be written as products of the previous ones. But when n going to lot, there are an infinite number of objects. Okay? So this immediately tells you that if you want to rewrite this problem in terms of these invariant singlet variables, you got to introduce not one radial coordinate but infinite number of them. Okay? But this collection of infinite number of invariants of the matrix, so what you want to write down, just follow me example of what I did. There was an original wave function which was a function of the matrix and time. That's what wave functions are, and you want to write this as a wave function of these things, trace m square, and what I call angular variables. The angular variables are the parameters of a unitary transformation which typically diagonalizes this thing. That's one choice of these angular variables. Doesn't matter what those are, but the important thing is that you got to keep this infinite number of them. And a good way of organizing this infinite number of singlet variables is, again what Shotto taught you, is to introduce the density of eigenvalues of this matrix. So here we are lucky, you got just one matrix, single matrix, Hermitian matrix can be diagonalized, and it can be diagonalized, you get n eigenvalues. So what you do, you diagonalize m, and so m now becomes a diagonal lambda 1 to lambda n. Each of them are dynamical variables, each of them is a function of time, these are not numbers, right? So I mean in the Schrodinger picture of quantum mechanics, these are just some real numbers. In the Heisenberg picture of quantum mechanics, or these are just some operators, in just some numbers, And in the Heisenberg picture of quantum mechanics, these are operators which are dynamically evolved by the Hamiltonian. And so you introduce density of eigenvalues, say in the Heisenberg picture. Forget about the T, I mean this picture is not very important. Let's do Schrodinger picture. So this rho of x delta minus h bar, this explained is the density of eigenvalues, and then you got to make a change of variables from these to the density. First you have to make a change of variables from these to those. You learned how to do that. There is a van der Monde determinant which comes in making that change. That determinant has to appear. That van der Monde determinant is an analog of this r raised to the power n minus 1, which was there in the transformation from Cartesian coordinates to polar coordinates. Here it's a little more complicated. There is this van der Monde determinant, which is all this beautiful story of repelling eigenvalues and stuff like that. But no matter what, you know what to do. So what you want to write down is the Hamiltonian, which is the variables of this Hamiltonian, which are functions of this thing. Is the density of eigenvalues is sometimes called a collective field, and the conjugate momentum to this eigenvalues pi of x is nothing but minus I del rho of x in the Schrodinger picture. And there are techniques to know how to calculate in this model this Hamiltonian. Just one thing you notice which has happened in this case, which did not happen for the isotropic harmonic oscillator. In the isotropic harmonic oscillator, I started out with quantum mechanics of n particles which are living in a harmonic potential. Okay? And the singlet sector was also a quantum mechanics of a single particle whose coordinate was r. Right? Here I started out with quantum mechanics of n square degrees of freedom, which were represented by this matrix Mij, and when I looked at the singlet sector of the theory, what I ended up is the quantum mechanics of a field. It's a field in one dimension. Okay? But there is no n square anymore. Somehow all this n square got packaged into an extra dimension. So x is actually an emergent extra dimension. It appears that this theory in the large n limit behaves actually as a quantum field theory in one space dimension. We started with quantum mechanics of n square degrees of freedom. We end up with quantum field theory in one dimension. Okay? This happens to be a very interesting quantum field theory, but I'll not talk about this anymore. This comment I wanted to make because this will be important in the second lecture when I talk about the ADS. This is the root cause of the ADS-CFT correspondence. Okay? So let me go back to this and show you an application to an infrared fixed point. We had discussed an infrared fixed point So the Lagrangian for this model is phi square is defined by of this model, and I want to look at the RG flows and the phase structure of this theory. In the large n limit, what I'll show that all you need is this formula in order to solve this model. So write So let us write action integral d dx on this thing and write this as S0 plus H0 plus I will just use that same notation b of x integral b of x d dx, where b of x I have written as phi square of x whole square 1 upon n. I have just stuck on 1 upon n there. Okay. Now this is the product of phi's. So if I were to do a Fourier transform, this will be of course a complicated mess, and we actually saw that there are these 4 momenta and all kinds of things. But I'll still write the Fourier transform of this thing as say b of q. So that is just defined as d dx e to the I q x d q dot x d of x. And S naught is this part of the action. Okay. So let's calculate the 2-point correlation function of this operator B, or equivalently of this object B of Q. So clearly by translation invariance, the only 2-point function is going to be thing with opposite momenta. So this by definition is B, let me call it K. B of K, B of minus K, exponential of half G. Oh, I'm sorry. There is no square here. So this is like, let me write this as B square. So it's just phi square. Minus G ddq with g equal to 0. This is clear because all I have done is that I have written this in the path integral. So this would be in the path integral d phi e to the minus s naught minus half g b b, and this thing with g equal to 0 is the thing is the average with the weights just e to the minus s0, just written a trivial equality here. Okay. And then what I do, let me expand this at 0 minus half g integral ddq at 0 plus 1/8 g square da 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 da. Okay, when the thing brought down twice. But now I know at large n this formula should hold. So therefore, what this means that this 4-point function can be cleverly factorized into 2-point functions. Remember, the 4-point function, what this thing tells you is that, for example, if I have a b1, b2, b3, b4, that is going to be b1, b2, b3, b4 plus b1, b2, and then there is an order 1 upon n, b3, b4 plus permutations, and there are things with 3 of those and so on and so forth, right? But in this case, in the 1-point function of phi square properly defined is just 0, because it's like in the vacuum there is no 1-point function of the operator phi square. Okay. So the only the important term that comes is the set of terms which just come when the 4-point function is written as a product of 2-point functions. So let me define the this is the 2-point function of the theory at g equal to 0. And if you look at this, you will get a nice recursion relation which tells you that the 2-point function, so this because, and G, like G K is at G, so you can easily derive that G of K is G0 of K. Let's get the signs right. In the large n limit. So, there is a very simple formula for the exact Green's function of these operators at some value of g in terms of the Green's function when the coupling is 0. Okay? Now, so what this immediately tells you, so if you look at this term here, that term was g upon 2n integral ddq b of q b of minus q, right. So, if I want to look at what is the effective coupling, the effective coupling of the theory, the effective coupling is defined as that object which you just stick in and just do basically a classical theory with. It is not very easy to see that the effective coupling in that is then given by G of k, it is a momentum dependent effective coupling, is given by the following definition. And what you find by combining this definition with this is an answer for the effective coupling G of k is G0 plus 1 plus G0, no, just G, whatever I started out with this thing. Okay. I know I didn't quite explain this very well, but if you privately I can try to explain how that follows. Okay. This formula is very telling because of the following reason. B0 was k, was the b of k, b of minus k at 0, so that's like phi each b of k is given by ddq phi of q phi I of minus q. That was the definition of b sorry, k minus q. And using this definition, you can just calculate what this object is by using Wick's theorem, by doing the double contractions. And I will just tell you what that answer is. The answer is, this equation then becomes G divided by 1 plus G by 16 pi k for 3 dimensions. What is G of k? This definition tells you G of k is the coupling which you measure in the scattering of two of these objects, phi going into phi, it has some strength. That strength depends on the total momentum that is coming in, and G of k measures that. So, it is the effective coupling of the theory. And what you find from this formula is that as k goes to 0, G of k goes to 16 pi k independent of G. Might appear a bit strange. You started out with a theory with a coupling G, and you get an answer because k is very small. So, it cancels the G in the denominator when the limit k goes to 0. Okay? So, you might be a little bit puzzled, how did this happen? I mean, you started out with a theory with some coupling constant G, and then you said, aha, at some effective momentum k, I want to define what the, I want to figure out how strong is the coupling of the theory, and this tells you how strong is the couple. It sort of measures the amount of interaction when you throw in two particles scattering into two other particles, and you find, wait a moment, the answer is independent of G. But that is exactly what you should get for an infrared fixed point. Because if there is an infrared fixed point in the theory, this exactly, so this is Z equal to Z, and I have set m square equal to 0. So, I am already on the critical surface. An infrared fixed point means that I have two objects m square, and then there is a coupling G. There is a Gaussian fixed point at m square equal to 0 and G equal to 0. We already figured out just from the phi 4 theory that the flows near that Gaussian fixed points are away. So, it is a phi square whole square is a relevant perturbation, right. And what you find is that low energies, regardless of I start here or start there or start there, at low energies I always go bang to this fixed point and stop there. Does not matter where you start out here. Okay? So, this tells you that there is an infrared fixed point at a dimensionless coupling G0, which is defined as G0 by k as 16 pi, just some number. Okay? This is the analog of the Wilson-Fisher fixed point in the large N expansion. And this tells you that in theories like this, where of course, in order to reach that infrared fixed point, I have tuned the relevant coupling to 0, otherwise it would not have happened, otherwise it would just flown away up there. Right? So, I have tuned that m square to 0. Once I tuned m square to 0, does not matter what the high energy theory is. High energy theory is anywhere out here. The low energy theory is just governed by this fixed point. At that fixed point, by definition, the theory has correlation functions which are power law. And in my first lecture, I explained why a power law means that the theory has scale invariance. So, infrared fixed points in a theory represent points which have scale invariance. So, let me now discuss a little bit of the mathematics of scale invariance and the related symmetry which is called conformal invariance. Is invariance x going to some number times x. This is called a dilatation symmetry. And I will illustrate this with a very simple theory in 2 dimensions, 2 Euclidean dimensions, which is massless free scalar theory in 2 dimensions. So, in d equal to 2, you write down an action which is half d2x d phi whole square. The coordinates are x1 and x2, and phi is a massless scalar field. So, then you can see that this theory is invariant under x going to lambda x and phi going to phi. Clearly, there are 2 powers of x upstairs, 2 powers of x downstairs, and the lambda cancels off. Okay. So, classically this theory is scale invariant. But this theory actually has a larger invariance which is called conformal invariance. Let me tell you what conformal invariance is. To look at conformal invariance, simply let us define some complex coordinates. This is just a definition. What did I take? I mean, if I have 2 real numbers, I can always combine them into a complex number, and its complex conjugate. And then this action can be written as half integral d2z dz phi dz bar phi. Dz phi means del phi del z is dz phi. Okay. When written in this form, you immediately realize the following fact, that this action is invariant under all holomorphic or anti-holomorphic transformations. These are transformations where z goes to z prime, which is only a function of z, and z bar going to z bar prime, which is again some other function of z bar. So, the new z is not a function of z and z bar, but just only a function of z. So, then clearly this thing is like dz dz bar. So, if I replace z, let me call it some function f and some function g, it is clear dz phi dz bar phi is integral df of z dz bar d phi df of z dz bar phi, if I keep z bar the same, and similarly if I do not do anything to z but something to z bar, the same thing will happen. It is just this cancels that, right, by the fundamental, what fundamental theorem of calculus. Good. So, now if you think about it, we started with scale symmetry. This action which I wrote down clearly has other symmetries. It has symmetries under translations of z and translations of z bar. It has symmetries under the rotations of x1 and x2. We will identify what these things are. But then you say, wait a moment, this looks like an infinite number of symmetries. It is a whole function worth of symmetries. I can take any function I like and I find a symmetry, right. So, this thing is an infinite number of global symmetries. This is what is called conformal transformations. and in 2 dimensions. There is one interesting aspect of conformal transformations which will be important for us. That if you look at the distance between 2 points which are labeled by z, so consider 2 points z bar and z plus dz z bar plus dz bar, then the distance sometimes called the metric is clearly given by dz bar dz. This is the same thing as, so this is the same as x1 x2 x1 plus dx1 x2 plus dx2, because this is dx1 square by dx2 square by Pythagoras theorem. Okay. So if I make a transformation z going to f of z, this metric now goes to, call it z prime, then it just becomes del z prime dz bar dz prime, but del z prime is what? 1 upon, let me do it the other way around, z equal to f of z prime. So this is like f prime of z prime dz bar dz prime. So what these transformations do in 2 dimensions is it takes this invariant distance, the invariant under rotations of the 2-dimensional space, which is given by dx square plus dx2 square. I made a coordinate transformations of x1 and x2 of a very special form, which can be written as z going to any function of z, and the only effect of that on this invariant thing is that it brought down an overall factor in front of the new coordinate z prime and dz bar. This is called a Weil transformation. Which is why conformal transformations, which is defined by these in 2 dimensions, can be alternatively thought as Weil transformations which rescale the metric by arbitrary functions of z and z bar. Okay. It turns out, now we showed that at fixed points of the renormalization group, theories are scale invariant. It just follows from the fact that the 2-point correlation functions, I mean all correlation functions are power laws, and therefore they are scale invariant. It is a deep fact of a large class of 2-dimensional theories, something which follows for something called the Zamolodchikov's theorem, which I thought I will prove to you, but that will take too much, which tells you that for a large and physically interesting class of theories, of 2-dimensional theories, scale invariance imply conformal invariance. So in 2 dimensions at the RG fixed points, you get an infinite dimensional symmetry algebra. And let me talk about a little bit about the generators of the symmetries, which will be useful in the next lecture. An infinitesimal conformal transformation changes, say, z by a small amount. So z prime is equal to z plus some, say, like delta z, let me write it as delta z, and this contains an arbitrary function of z. This can be an arbitrary function of z, but which is small. So, let us write it an arbitrary function of z, but this is small. And similarly, there is the anti-holomorphic transformations which are given by this, given by z bar. Now, for holomorphic functions, it is a very useful basis. I can expand any holomorphic function in some basis, in a kind of a Laurent series expansion of monomials of z. So, I can write this, as a small parameter times z n plus 1 and sum upon n. Okay. N goes from, I know, minus infinity to plus infinity. This is the Laurent expansion of a function around some point. And then I see that if only non-zero is non-zero, all others 0, this delta z equal to z prime minus z is given by z to the 1 del del z acting on functions. If so, this is, I should not say delta z, I should write delta z is z to the n plus 1. So, delta of some function of z is, if that function is, this thing does not change, is given by z to the 1 del phi del z. So, acting on regular functions, we call these the generators of the conformal transformations. They have a name called Ln, and these are the generators of these transformations on the complex plane. It acts on any function of phi, and the operation on that function of phi, which is the result of the conformal transformations in the complex plane, is given by this. Let us look at a few of them and try to identify what these things are. So, let us look at, so what do we want to look at? N equal to minus 1, how about that? And similarly, there are things called, I will call them small l actually. So, let us look at L of minus 1. So, that is just del del z, right. Similarly, L bar of minus 1 is del del z bar. Okay. So, clearly L minus 1 plus L bar minus 1 is just given by del z plus del z bar, and by a change of variables you will find that this is same as del x1. So, this is the generator of translations in the x1 direction, and similarly I L minus 1 minus L minus 1 bar is given by del z minus del z bar equal to del x2. So, these are translations. Let us look at n equal to 0. There is only L0, which is z times del del z, and there is L0 bar, which is z bar times del del z bar, and of course, as you would expect, L0 plus L0 bar is x1 del del x1, L0 minus L0 bar is x2 del del x2, So, these are scaling or dilatation transformations. Okay. Sorry, this is not that. I am sorry, this is wrong. This one is scaling L0 plus L0 bar. This plus that is actually x1 ddx1 plus x2 ddx2. That's scaling. And I times L0 minus L0 bar happens to be del 1 del x2 minus x2 del x1. This is the angular momentum generator. So, this gives rotations. There is plus 1, that's d squared dz, and L bar plus 1 is z bar squared dz. And then what you find is L1 plus L1 bar is x square minus y square, x1 square minus x2 square ddx1. This is a bit complicated. No, just it's minus 2 x1 x2 ddx2 plus, I think I might have mixed up the signs. Some complicated transformations. These are called special conformal transformations. And if I write what does this mean? This means that del x1 is equal to this transformation is means that del x1 is x1 square minus x2 square, and del x2 is 2x1 x2, and the other one means del x2 no, that means del x1 is 2x1 x2, and del x2 is x2 square minus x1 square. I think there is a minus sign here and a plus sign there. Okay. These two can be combined into a single formula. These two. So, if I put back, there is always a parameter epsilon. So, this parameter epsilon just hangs on with all of those. So, this is the formula for the special conformal transformations. Okay. My time is always up, but all I wanted to impress upon you that at least in a very simple model for 2 dimensions, we showed that it is obviously scale invariant, it is also conformal invariant, and I stated without proof, it actually turns out that you can prove that for what are called unitary quantum field theories, scale invariance always implies conformal invariance by using a theorem which is called Zamolodchikov's theorem. One of the when I go to higher dimensions, what you find is that conformal transformations are no longer an infinite dimensional group. If there are no longer an infinite number of these L's, these Ln's are called the generators of a Virasoro algebra. If you calculate just from this formula the commutators of Lm and Ln, what you find is m minus n Lm plus n. This is the classical Virasoro algebra. What one finds that if one goes beyond d equal to 2, like d equal to 3 or d equal to 4 and so on and so forth, there is no such infinite dimensional group, but translations, scaling, rotations and the special conformal transformations, they combine and they form a single group which is called the conformal group, and that's it. It's a finite dimensional group. Okay? So next lecture I will talk a little bit about this finite dimensional conformal group in higher dimensions. I will argue why geometric realization of that together with what we learned from quite disparate things actually. The mathematics of the conformal group together with the physics of large n factorizations and classical limits leads to one of the most exciting developments in recent years, which is called the ADS-CFT correspondence. Okay? And I'll end by showing how this correspondence gives you a geometrical picture of the renormalization group flows. I think that should be